Okay, well, we see that the cylinder x squared plus y squared equals 1 is just an infinite cylinder of radius 1 centered at the origin, or centered on the z-axis, and it goes all the way up and down the z-axis. It doesn't have any limits. Now, if we wanted to do a finite cylinder, we could add to the x squared plus y squared equals 1 that like z is between -4 and 12. Then we'd have a cylinder like 20, right? But we aren't doing that because what we're doing is we're intersecting it with the sphere, x squared plus y squared plus z squared equals 1. Okay, so in rectangular coordinates, x squared plus y squared is less or equal to 1 because the region is inside the cylinder. So inside the cylinder, x squared plus y squared is less or equal to 1. Okay. Now the region is inside the unit circle. So we can just look at this region down in the xy plane. There's a circle of radius 1. And now what we can say we have points within this region for every x value between -1 and 1. Okay, so we'll just to be sure we have all the information. It's -1, 0, 1, 0, 0, 1, 0, -1. We take an x value between -1 and 1. I say we partition the interval from -1 to 1. There's a partition. We partition the x-axis. And then I've seen anybody drawing partitions. Okay. It's extraordinarily helpful in figuring out what your limits are. You do without drawing partitions, well, you get most everything, but you're going to understand it better if you use partitions. That typical partition then, typical interval of the x-axis would be here, and it would have a sample point, and you would have to partition y from here to here. The ith x interval We use x equals xi star as our value of x. I've explained this in more detail previously. Let's go back over it if you need to. Okay. On this vertical line, the y values inside the circle bounded by negative square root of 1 minus xi squared, xi star squared, and 1 plus xi star squared. It'd be a little hard to read that. Get that I out a little bit. And the reason for that is just Pythagorean theorem applied to this triangle or the similar one down here. If I enlarge that triangle, this side is xi star. This side has radius 1. This side better have some radius, have length 1 minus xi star squared. Okay. I mean, you see that triangle a lot. Those different coordinates and stuff. Okay. It's just fundamental thing you got to know to be able to even get started with volume elements. Most of them that you're going to see in this course involve that, or at least a large portion of them. You have to understand the geometry of that. You have to understand the Pythagorean theorem. You have to be able to apply it. Okay. It leads immediately to this. Okay. I've seen a lot of people writing things like 1 minus xi, or just 1 minus x, still 1 minus x squared. Tells me you're doing it by imitation without thinking. Okay. And all you have to think about is Pythagorean theorem. Okay. The person I think made the highest score in the test made that mistake on an arc interval, length of an arc in square things. Okay. Did almost everything else beautiful. So it's easy for somebody who's really pretty much on top of everything, as many of you are, leave off those squares because you're not thinking. Because you remember it looked like this, and you don't think about why it is what it is. Okay. That's why you want to build these things from the ground up. Make sure you understand every detail. All right. Now let's see if I've recorded any of that. Yeah, still recorded. I wish the thing would keep the recording indicator up there. Okay. So now our circle -1 less or equal to x less or equal to 1. If you know what x is, you know that y goes for that x from negative square root of 1 minus y squared, x squared, sorry, to the square root of 1 minus x squared. And eventually, if you write out partitions enough, you understand how that relates to partitions. Okay. It's because on the ith interval, you're going to have upper limit of square root of 1 minus xi squared. And remember that what you're doing is you're taking then the whole strip corresponding to this one interval in the partition of your x values, and you're going to partition it. So that you're going to partition y between square root of 1 minus xi star squared and 1 plus square root of xi star squared. That's when you're inside the region. Okay. Now about z. Well, okay. You partition the x interval, and then for each x interval, you partition the corresponding y interval, and you end up with a general interval down here in the plane, which will be your ij area increment. With sample point xi star yj star. Now, I haven't written here that xi star yj star is your sample point within the ij interval. You should understand that, okay? Now, the sphere consists of all the points inside, right? And really, I should have written, no, it said volume of the intersection, should have said volume bounded by the intersection, okay? That intersection is going to have this restriction on x and y, x squared plus y squared has to be less than or equal to 1. And I should say interior, or I'll say inside the circle x squared plus y squared is 1. Just getting all the words right. Since x squared plus y squared plus z squared is less than or equal to 1 inside the sphere, if you have the point xi star, yj star, you're going to get z less than or equal to 1 minus xi star minus yj star. Now what you're doing here is you've taken everything above and below this xy increment here, okay? And that using the sample point xi star, yj star, it hits the sphere above or below whenever xi star squared plus yj star squared plus z squared is equal to 1, right? So you end up with z squared less than or equal to 1 minus xi star minus yj star squared, xi star squared and yj star squared. See, possible to write that down without putting the square on it, okay? Here I should catch that. Okay. So the solution to this is square root of 1 minus xi star squared minus yj star. The negative square root of that is less than or equal to z, is less than or equal to the square root of 1 minus xi star squared minus yj star squared. It might be a little hard to read. I had to squeeze it in. That should be pretty obvious. Okay. If you want to look at the video, you can find that pretty easily. And it should be pretty clear on the video. So we have our description. The intersection of the sphere and the cylinder. There it is, and there are your limits on the interval. Now, it turns out that the intersection of a sphere of radius 1, centered at the origin, and a cylinder of radius 1, centered at the origin, is just a sphere. Okay? The cylinder fits all the way around the sphere. Okay? If we changed it slightly to where the cylinder was x squared plus y squared less than or equal to a squared, say, where a is less than 1, then you have a bit of a restriction, and it should be clear that the description would be assuming a is positive. And let me rewrite that restriction on a. Said absolute value less than 1. Yeah, that's fine, but let's just make a positive. So 0 less than a less than 1. Then your cylinder, your circle, is a circle of radius a. You just do everything I did for a circle of radius 1, but use a radius of a. And you're going to find that y is bounded by the square root of a squared minus x squared. Then I get a squared a minus x squared below, and the square root of a squared minus x squared above. Then z, well, for any x and y inside the cylinder, there's going to be a point above it and a point below it on the sphere, right? And it's the sphere that bounds it above and below. The cylinder isn't bound. So you get z less than or equal to what? back to your equation. Well, it doesn't matter. Okay. Here's your equation. You're still going to get -1 minus x squared minus y squared less than or equal to the square root of 1 minus x squared minus y squared. A isn't going to be involved in the limits on z because A has already limited your x and y. X and y are already limited by these inequalities to being inside that circle of radius A. If you're inside that circle of radius A, you're still going to go up to at a point x, y inside because of these inequalities, the circle, you're still going to go up to 1 minus the square root of x squared minus y squared. And if it was a bigger sphere, radius big R or something like that, it'd be big R squared minus x squared minus y squared. Okay. Now, to do this with less trouble, spherical coordinates. We don't want to do spherical coordinates. I mean, we could. It's interesting to go ahead and try. It's actually simplest in cylindrical. Circle in the plane perpendicular to the cylinder. We're going to go ahead and use A. It doesn't matter. We can use 1. It's fine. But if you use A, it's more general. Okay. R, your arc coordinate, your distance from the origin within that circle, can't be bigger than the radius of the circle, less or equal to A. The theta coordinate, the angle between the vector from the origin out to the point on the circle, has to be between 0 and 2 pi. Okay. And if you go from 0 to 2 pi, you get the whole circle. We do a wedge out of the circle by restricting theta, but we're not doing that. Okay. And then what? I'm just going to tell you, it's just square root of, instead of 1 minus x squared minus y squared, it's 1 minus r squared. Now, I see a lot of places, I mean, I've seen them, and I'll always do at this point, where people are using x's and y's and z's inside, or x's and y's in something that's in cylindrical coordinates. X and y isn't there in cylindrical coordinates. Now, one person went ahead and used sine squared theta and cosine squared theta instead of x squared and y squared. Okay, and that can be valid. Might not be the simplest thing to do in this case, but it can work. Okay, it's not a bad idea. Okay. So the integral, in this case, we're just doing the volume. So the volume increment, no, we don't want to do dr first. We'll do rd theta dr dz, theta from 0 to 2 pi, because that's the first thing we're integrating with respect to. R from 0 to a, and z, and the square root of 1 minus r squared to the square root of 1 plus the negative 1 minus square root of r squared to 1 minus to the square root of 1 minus r squared. I'm saying the plus because somebody had pluses on these r's, otherwise had the right interval. Okay. If you think about it, think about why plus r squared wouldn't work. Plus because of the Pythagorean theorem, also because 1 plus r squared gets bigger as r gets bigger, and the sphere doesn't get higher as you move further from the axis, okay? Your integral up here, you need that there. This is a little bit long to write out and get all the limits in here correctly. But, you know, you're just doing, first one's x, second one's y. Now you get a square root of 1 minus x squared minus y squared, square root of 1 minus x squared minus y squared. And then from, it'll be hard to get this in there. I need to write it bigger. So I'm going to give myself more room and rewrite it. I'm going to give myself all this room. This last integral was from 1 negative square root of 1 minus x squared minus y squared, the square root of 1 minus x squared minus y squared, and that's with respect to z. Takes care of our z inequality. If you got the inequalities, you just write out the integral. Very easy. If you don't have the inequalities, you're unlikely to get the right integral unless you're just imitating something very similar that you've seen. Okay? You want to reason it out. Okay, then we integrate from square root of 1 minus, square root of squared minus x squared. Still hard to write this clearly. To the square root of a squared minus x squared. That's with respect to y. Negative a to a with respect to z. If we then want to find the mass of this object. Now, there are other things you can intersect. What if you intersect a cone with a sphere? Okay. Cone with its apex at the origin coming out like this. You've seen it. It's in the example, it's in the text, and it's in some of the problems. I'm not sure it was assigned. You should be able to intersect a cone with a sphere. And you just got to restrict phi and use spherical coordinates. Very easy, but you should write it out in all 3 coordinate systems. It's not that hard to write in the XY coordinate system, but it's simplest in the spherical. You need to make those comparisons. But mainly, you need to write out the inequalities, understand them, and understand the partitioning process. Okay. Because if you understand the partitioning process, then you understand that if we want to get the mass of this region, and you got a mass function, you just multiply the area increment by the value of the mass density function. Okay? If you want to find the moment of inertia, you just multiply the area integral by the mass density by the distance from the axis of rotation, as we talked about last time. If you want the centroid or the center of mass, Well, your book tells you what the integrals are, tells you why. You understand what we said about the moment of inertia last time? You understand what I'm telling you here? It's just what you plug in front of your area increment, okay? For your volume. It's a mass density, it gives you mass. If it's R times the mass density, it gives you the moment of, well, sorry, R squared times the mass density gives you the moment of inertia. Not the z-axis as far as your distance. Okay? So this stuff comes together pretty nicely when you do the section on the center of mass and so forth. Okay? Now let me regroup. I was a step ahead of where we needed to be last time. I should have talked about this first and then but I think it works either way. I think, if you understand, the main focus from last time is focus on what you have in every increment of volume. Okay? That's it. Focus on one increment of volume and then write the inequalities that span your increment of volume. Think about the partition. Preferably write out the partition, write out the details, draw it, draw pictures. I don't see enough pictures. I've said that before. Because the pictures tell you what you're doing. That's where most people, okay, 98% of the population, or 90% of engineers in the world would understand things better if they draw the pictures. Probably, majority of them won't understand anything if they haven't drawn the pictures. Might be able to imitate, but they can't do it. Okay, you want to be one that does it. You can find time to develop the skill. Okay. Okay. Now we want to talk about vector fields, and let me just pause for a second. Okay, for any scalar function of x, y, and z, it's easy to well, the derivatives are easy to take, and it's easy to calculate the gradient, right? And what's a gradient? Tells you the direction of maximum increase and the rate of maximum increase, right? Tells you how fast it's increasing in the direction of maximum increase. So take this vector field. And the gradient, I'm not going to write it all out. Partial respect to x of I plus partial respect to yj plus partial respect to z of k. Dot, and we I started saying for any scalar function, right? And I wrote a vector function. So what I was about to do is the divergence, and we're not talking about that yet. I mentioned it last time. We can do the del dot v. We can't do del of v because it doesn't tell us how to combine the i's or the j's. Unless we have something like a dot or a cross product there. Okay. Let's take this one. x squared y cubed z. The gradient of v is 2xy cubed z times the I vector. That's 3x squared y squared j y squared z times the j vector plus x squared y cubed times the k vector. It's a very easy calculation when you're asked to do gradients. You haven't done them in a couple of weeks. You got to remember. Okay, very easy. Okay, well, that's a vector field. So I could plot that vector field at a number of different points. Let's say at the point one, 1, 0, and I'm just going to do this in the XY plane. Point 1, 1, 0, then you're going to have 2i plus 3j. Make sense? Okay, so you got a vector. Two I plus 3j. If we go to the point 1, 0, 0, then our vector is 0. Okay? Because x, every one of these except the last one has y equal. Well, all of them actually have y equals 0. So y is 0 here. So they're all 0. So you got nothing. Go to 1, negative 1, 0. Then what do you have? X is 1, y is negative 1. Well, you're going to have 2 times 1 times negative 1 cubed. Uh-oh. I'm saying we're in the XY plane, and I'm going to have to change my mind about that. I'm also going to, I'll stick with it. I'm just talking about mapping out a vector field. Okay, if you've had differential equations, you know directional fields. Just give you an idea. Do a gradient. Okay. Okay, so at the points be 1, 1, 1, 1, 0, 1, 1, negative 1, 1. Okay. If you got 1, negative 1, 1, you're going to get negative 2i. But you're going to get 3j. I'm not drawing these real accurately, just giving you the idea. What generally happens in the first quadrant is your I component is going to reverse. Go to the second quadrant. I'm just going to tell you, if you got a vector field, you can map a bunch of different points. Okay. The first problem you're likely to have is to calculate the gradient field. Just find the gradient field. You don't have to graph it. Just demonstrating the gradient field can be graphed. Okay, you graph 100 different vectors at various points. Get an idea what the field looks like. Okay, remember the fields that I drew last time? One of them kind of a circulating field, right? We're seeing that. Just talking about circulation and divergence and stuff. The circle is a flow line. And these are vectors. I don't remember what specific function I gave you, but if the function here is yi minus xj over x squared plus y squared, let's just say this is your vector field. Then you're going to have the same picture. You're going to have the same flow line. You're going to have a circular flow line centered at the origin through any point. So if I could take a point out here twice the distance from the origin, circle got out of hand, but you get the idea. Okay. What's happened out here? Okay. You're going to have a yi minus an xj, which has magnitude square root of x squared plus y squared, right? Magnitude of the numerator is the square root of x squared plus y squared. The denominator is x squared plus y squared. So the magnitude of the vector is going to be the square root of x squared plus y squared. Okay? So if we go out to this circle, you don't have to be able to do that, but if you go out to this circle, that's going to make every vector is the reciprocal square root of x squared plus y squared. It'll make every vector a little bit shorter. Every vector will be square root of 2 over 2 or 0.7 times as long as the vector's on this circle of radius 1. So you can visualize a bunch of flow lines going around here, a bunch of flow lines going around here, but slower flow. And then a bunch of flow lines around the circle outside. The flow lines are the circles. The vectors are going to decrease in magnitude as you go out. It's kind of like water going down a drain, isn't it? Like a vortex. Now, I don't think that's the right expression for an actual vortex in a bathtub or something like that. I don't think energy would be conserved there. But anyhow, there it is. The other vector field that I illustrated was one that had, you can use circular lines. I mean, we can use circles to define it. And I think it was kind of like this. In toward the center. I might have used one out from the center, but I think I kind of started with the idea of a gravitational force pulling things in. Okay. And if it's gravitational force, it's going to fall off. In inverse square force, it's going to get a lot shorter as we go out here. In this case, we call these circles orthogonal trajectories. And then the flow lines are just going to be the two axes and the lines at 45 degrees, and then a bunch of other flow lines. Since the vectors are always going to be pointing toward the origin, the flow lines are always going to go in toward the origin, right? Anybody watch the Artemis launch? Anybody aware of it? I knew that it was the window started at 6:24. And I did have a few minutes to start doing a few things on the computer. I thought, oh, geez, I better tune into that, see where they are in the countdown. They just blasted off 3 minutes ago. I love to see rockets go off. I mean, it just lets me out. Back in junior high school, when they launched first John Glenn, first orbit in America, put us all into the auditorium and had one television set. A pretty big television set for those days, because maybe television sets weren't very big then. It was in black and white. We could afford color in those days. They existed, but nobody had them. They're really expensive. It came down pretty quickly. A couple of years later, everybody had it. The the thing's pretty cool because he's up there and they got to cut him short. And it turns out they had a problem with the heat shield. They weren't sure he was going to make it back alive. And then there's this big delay when he's supposed to be back and the cameras are, he's not there for a couple of minutes. And people are getting really worried. All of a sudden, boom, there's a picture. Just full moment. Okay, well, that's just background. If you're orbiting the Earth in a circular orbit, you're going along an orthogonal trajectory. Okay? They don't always do an orthogonal trajectory. You can do elliptic. As a matter of fact, these guys are probably in an elliptical orbit because it's the only way they're going to get to the moon. Stay in a circular orbit around the Earth, close to the Earth, and not getting closer to the moon, but you're not using any energy either. There's a lot to the orbital mechanics, but since they're moving perpendicular to the force of gravity, gravity's not doing any work on them. It's only changing their direction. Okay, if you're in an elliptical orbit, coming out like this, when you're coming in, gravity's speeding you up because there's a component of gravity in the same direction as your velocity. They're not parallel, but there's, gravity's not always perpendicular. And when you're going away, there's a component in the direction of motion that's opposing the motion, so it slows you down. So you come in this ellipse and you come in and you get close, you're going really fast, then you go out really slow. If you want to go to the moon, you boost yourself right here and you go out a little further. And then you boost yourself again when you get here because that's the most efficient place to boost yourself until you get an orbit that intersects the moon. It's not exactly what they do because of what they're trying to accomplish when they get there. Okay. But that's kind of the principle. It's pretty neat. Fluids, all kinds of applications of circulating fluid. Okay. This is all really important stuff. Um, I'm just looking through and I normally look through these the night before, but it wasn't possible. Um, there's a lot of stuff here. It says if you got an electric field, the gradient of the potential. Okay. Like if this is your potential function, this would be the corresponding electric field. That's all you got to know. Now, if you're in my physics class, yeah, you got to know a lot more than that because that's what we're doing. Okay. But that should make a connection. Anybody's taking physics. Okay. That's like your voltage function or potential function. Take the gradient of it. You got your electric field. And you can integrate the electric field to get the voltage, but line intervals, I decided to wait one more week to do those. Okay. Just because y'all are running into some obstacles with the volume integrals. There's a problem that actually uses the, come on, trying to close you out. Cut this. Jeez. Either I'm losing my ability to navigate a trackpad or this computer's getting really fussy. Could be either. We'll see how things shape up next week. Okay. Well, that's pretty much background of what you need to know about vector fields. They're functions, evaluate them, plot them. Okay. If you're asked to do it. I don't think you're asked to calculate the orthogonal trajectories or flow lines of fields that you get. That's one thing I was trying to check, just make sure we weren't doing that. Okay. Quickly. Let's say that I do have a path through here and I talked about it. So let's say you've got an elliptical orbit going in this direction. This is conceptual background for line integrals and get your mind working on them. Okay. Take an increment. Let's say this is a function R of t. You're used to using R of t for a vector function, right? Then a delta ti interval with a sample point ti star gives you a vector at this point. So let's just say your vector is R of Ti star. You also have this force field. There's gravity pulling you in. And that force field is toward the center. So on this interval, you have your R of Ti. You have your force F, which is the force field evaluated at the point R of Ti. Remember, R of Ti is just a vector from the origin up to this point, right? So that's a force at this point. And it's Ti star in both cases. It's your sample point. Then the work done on this interval by the force F on whatever it is that's moving here. I'll call it delta W sub I, the work done and what I'm saying here isn't quite right, and the notation gets a little more difficult than I was planning. Now, this isn't really R of Ti. R of Ti is from here to here. That would be your delta R vector, the difference between the R vector from here to here and the R vector from here to here. So this is your delta R vector corresponding to this interval, delta Ti. You sum these up over the whole ellipse. That in a gravitational field, you're going to get zero. But if you sum them up from, let's say, here to here, you're going to get the work that's done by the gravitational field. Okay? I could detail that. People got to have a mass and all kinds of stuff. But the concept is you can do this line integral from here to here. Okay? And tells you how much energy, how much kinetic energy the spacecraft gains. Okay? Turns out that kinetic energy gain is equal to the change in the value of the potential function, whose gradient is this gravitational field. Okay? So you don't have to do that line integral to figure out how much work. Just take the difference in the potential function. And that's a big deal. It's conservative vector field. And that comes up next week. Want to give you a little head start in that, and I kind of used some bad notation there. Apologize for that. Should be in better shape next week. Okay?